So what physicists have done to replace this problem with the singularity of the Big Bang is that they have replaced part of this evolution law early in the universe. So you take the normal Big Bang theory up to a certain moment in time, depends on exactly how you want to do it, then you add a different evolution law and you use this evolution law to go back further in time. This gives you a different initial state, and it can get rid of the singularity, and it can have all kinds of other consequences. So you change the equations, and then, as I said, you'll always get an initial state that then fits together with those equations to give you what we actually observe. And there are lots of different theories that have come out of this. For example, there may not have been a Big Bang, there might have been a big bounce. So there was an earlier universe which contracted, and then it didn't go to a singularity, but it just shrunk to a very small size, and then it began to expand again. There could be cycles. Roger Penrose, for example, has a model for a cyclic cosmology. There's an idea that's called asymptotic silence, where basically the early universe was just sitting there for a really, really long time, not doing anything, and then suddenly it decided it'd expand. This also gets rid of the singularity. There's the no boundary proposal from Hartley and Hawking, where you basically get rid of time entirely, so there's only space, 4 dimensions of space. Some think maybe there was neither space nor time, there was just a pre-geometric phase, maybe some kind of a big network that had to condense into a form where it would give rise to something that approximates space-time to a very good precision, 5-dimensional black holes, string gases, and so on and so forth. It's a really long list. But those ideas all work the same way. You change the evolution law somewhere back in time, and then you have a different initial state. Now, what's the problem with this? Well, as I said, a good scientific explanation must be simpler than the observation it's trying to explain. And the problem with all those theories for the early universe is that they make a simple story more difficult. But a good scientific explanation should be as simple as possible, and you shouldn't add any unnecessary assumptions, no matter how much you would like there to be a cyclic universe. It's as Laplace put it, I had no use for this hypothesis. We also don't really have a use for the hypothesis of an infinite number of cycles. It's absolutely unnecessary to explain what we currently observe. And so this is why I say all those stories, they're basically tales, they're creation myths written in the language of mathematics. They're mostly not wrong in the sense that all those physicists, I mean, it's not like they're dumb, right? They make a big effort to get a theory that actually agrees with observations. Of course, I mean, there are some people who argue that this or that idea doesn't actually fit with observations, but that's a little bit beside the point. Mostly they're trying to actually get the observations out right. So they're not wrong, but we can't tell that they're right because they just add this unnecessary structure at a time where we don't actually have any data. So basically, you can believe whichever one you like, and my friend and colleague Tim Palmer has dubbed this ascientific. It's not that it's non-scientific, it's just that science can't actually tell you which is the right idea. Will science ever be able to tell us which one is the right theories for the early universe? I'm not so sure. I'm pretty sure that we'll be able to improve over the theories that we currently use. They have other shortcomings than the Big Bang, so I'm pretty sure we'll be able to come up with better models than this. But will we ever be able to figure out how the universe began? I'm very skeptic because of this issue that there's just no justification in science to attach a more difficult story before a simple one. If the early universe was very simple, then you can add all more difficult explanations before this, and we would never be able to figure out which one is the right one. So did the universe begin? we don't know, and we may not never know. So we'll continue with the question, was the universe made for us? To which I think the answer is no, for all we currently know. So first I think I have to put this question into context. Physicists, as I said, we don't really like to talk about life and so on. But in cosmology, we often talk about the preconditions for life. For example, carbon is often used as a precondition for life, but some of you may think maybe this is already too specific. At the very least, you'd need something like a sufficiently complex chemistry, or indeed the possibilities for any structures to form in the universe. And this is all not life in and by itself, but it's something that we believe to be necessary for life to ever come into being. And so the reason physicists talk about this question, like, was the universe especially made for us? Like, do we have a special place in this universe? Comes from the observation that for some slight changes to the constants of nature, it would not be possible for structures to even form. It would not be possible to form carbon or any kind of sufficiently large molecule. The most famous example may be the structure of the carbon nucleus, which is a prediction that was made by Fred Hoyle. So he figured out that for carbon to be produced in stars, the carbon nucleus had to have a particular structure, it had to have a particular resonance, and that was later actually discovered. So I think one way to look at this kind of prediction is to say that the observation that we ourselves exist is also an observation, and that is good for some things. For example, for the observation that it must be possible for stars to produce carbon. There are some other examples where some changes to properties of the constants of nature or nuclei and so on would eradicate life as we know it. A particularly simple to understand example is the cosmological constant. So the cosmological constant is that thing which makes the universe expand, or actually makes the expansion of the universe accelerate. So if the cosmological constant was very large, then it would basically immediately rip apart all the structures in the universe. So stars and galaxies could never form. This is if the value is positive. If the value is large and negative, so the absolute value is large, but the sign is negative, then the universe would immediately recollapse after the Big Bang. So again, there's no way that structures could have formed. So again, we see that just the observation that we exist, odd as this sounds, tells us something about the cosmological constant. It's a similar story for Newton's constant. So Newton's constant sets the strength of gravity. If gravity is too strong, then stars burn out too quickly, and so on and so forth. There are lots of books that have been written about this. I'm not going to go through the entire list of examples. They all basically work the same way. You take a particular constant of nature, you make a small change to it, you figure out what happens to all the physical processes that we know of, and then you figure out that some of the preconditions for life are no longer fulfilled. Which brings up the question, can this possibly be a coincidence? It looks as though making these small changes makes it appear very unlikely that our universe would have had just exactly the right values for the constants of nature so that life can exist. So there's a big problem with this argument, which is that if you're talking about the probability of something, you have to quantify this probability. So normally, when we talk about the probability of, say, throwing dye, we have a probability distribution that, in principle, we can either derive from a model for the dye, or we can just collect it by throwing dye many times and collecting the data. So we know it's 1/6 for each of the different phases to come up. But when it comes to the constants of nature, we don't have any probability distribution. So if someone makes a statement like, it seems to be very unlikely that the constants of nature would just have exactly the values that we do have, that's a completely meaningless statement because we can't quantify this probability. So it's not a scientific argument. You could certainly say, and people have made this argument based on Bayesian probabilities, I find it surprising that the values of the constants are so as to allow for the existence of life, and that's fine. You're free to find surprising whatever you want, but it's not a scientific argument. There is another issue with this argument, which is, for one, it's just wrong, and that may be it may come somewhat as a surprise, because some of those topics that we talk about in the foundations of physics, it seems that nothing ever changes. We've been talking about some of those things for hundreds of years, like determinism, indeterminism, nature of time, and so on. But this is an example where people have actually come up with new arguments. For example, they figured out that there are actually other combinations of the constants of nature that do seem to allow for the preconditions of life in some form, and those are not the same as in our universe. One example, as I just said, Hoyle figured out that the carbon nucleus should have a particular resonance, so as for carbon to be produced in stars, but there are other possibilities, other ways you can make this happen, and recently someone has come up with a different way to do it, where the constants of nature are not the ones that we have in our universe. There are also people who have argued that we actually don't really need what's called the weak nuclear force. So the weak nuclear force is one of the fundamental interactions that we know of. It's responsible, for example, for radioactive decay. And some people have argued that we actually don't need it to create all those structures that we see in the universe. They call this a universe without the weak force. And they say in such a universe you'd still be able to produce sufficiently complex chemical structures. So it just seems that it's just not the case that there's only one particular combination of those constants. I also think that part of the reason why physicists fall for this kind of argument, like the universe is really, really special and we need this exact combination of constants, is that they tend to think that complexity is rare. It takes something to create it, whereas I think it's exactly the opposite. Like, complexity is the thing that we generically get if we combine all those physical processes. And this is actually an argument which was made beautifully in Stuart Kauffman in his book At Home in the Universe. He basically says if you combine sufficiently many things and you just give it time, then complexity will come out of it. I think that physicists they're not familiar talking about complexity at all, so for them this kind of thinking is a little bit alien. But I believe if we understand better how complexity comes about and how chaos works and all that kind of thing, we'll probably find there are many other examples of combinations of constants of nature that would also give rise to preconditions for life. So I really think it's more likely to be the rule than the exception. So was the universe made for us? For we currently know. No.